Welcome all to today's Passive House Alberta Building Better in Alberta webinar. My name is Frank Crawford, and I'm the Education Committee Lead for Passive House Alberta. And today, unfortunately, you're stuck with me, and we'll be learning all about some low carbon, low cost made in Alberta building envelope assemblies, which is based on some research and a grant project that Passive House Alberta received. But before that, we'll hear from our sponsor, Alberta Eco Trust and NBIX. And because this topic ties in very well to a new program that they have underway recently. And to talk about that, we have Juan Monterosa, who is the Senior Project or Program Manager at Alberta Eco Trust and the Emissions Neutral Building Information Exchange. So take it away, Juan.
Yeah, thanks a lot. So today I wanted to talk about our research project that just came online, and actually, like, the expression of interest just closed last week. So this is a good time to kind of get everybody ready and excited for the next round, which will be opening up in July 13th. So the project that we're looking at, the research project, is Getting to Zero. And the idea for this project really is to try capture um, as much data as we can for three different streams within building and construction. This project was essentially, we took some inspiration from our friends in Zebex in the Lower Mainland with their near zero research project, with their different streams as well. So we've been fortunate enough to kind of learn from them and help build the program based off of their work. So there's three different streams that we are looking at. There is the stream one, which is for operational emissions, where we're collecting data for new construction in Part 9 buildings, anything going with low to zero operational emissions. The second stream, which is going to align a little bit with the work we're going to be hearing about today, is embodied emissions. So collecting data, same thing in terms of the design and construction for Part 9 residential projects for low carbon materials. And the third stream is looking at combined heat pump and natural gas heating systems. And again, getting data, and the biggest part through all these is finding costing data for each of those, but also like trying to understand really like the lessons learned throughout the process. So this is a bit about like where we're trying to get to and look at the current practices, both understanding where kind of like trying to find the spectrum, I guess, of like buildings, whether it be, just if you're just meeting tier one, tier two right now, what does it take to get to that tier four and up? If you've already been doing tier four and up for a while, like what does that look like as well? And I think we're trying to speak about kind of those different stories are very important. The other portion of it for embodied carbon and emissions, it's really just to kind of, there's been a lot of great work done by Builders for Climate Change. Um, and I think the reporting that's done through NRCan, that we could see what's happening across the province. And from our end, we want to see kind of a snapshot right now in Alberta as well. And combined heat and natural gas, looking at again kind of like that Alberta lens that we talk about through our NBIX work. So eligibility, I won't go too much into these because I'll provide the link where you could go through and see the full webinar on this, and also all the documents you could read through. But the primary things for these ones are like the eligibility is we're looking for designers, builders, consultants, developers. So it's not looked at for homeowners. This is really looking at industry to help us provide some of that information. So the ineligible participants. Projects, all the projects have to be in Alberta. The project end date is a maximum of 24 months after the start date, and they are Part 9 buildings, so those single family, but also there's some multifamily that fall into that as well. We're not looking at commercial projects for either of the streams. If you're in stream 1, you're ineligible for stream 3, but there is an opportunity to look at stream 1 and stream 2 together. So the requirements, I'll put these up here. And it is essentially looking at questionnaires for design and in construction and getting the information both on the embodied carbon calculations, the operational carbon calculations, and also looking on stream 3 of the sizing of the heat pumps, but also looking at the pre and post energy modeling for that as well. The payments for all of the data, so for each one of the streams, this is how we're trying to entice applicants to come in and give us the um, very detailed drawings, energy models, and costing. So up to 25,000 available for stream 1. So again, there's 15 there for if you're at tier 4. If you're at tier 5 through the code, 20,000 and additional $5,000 if you're going with a ground source heat pump. With embodied emissions and the embodied carbon is up to $10,000. So all projects will get 6,000 from the onset. And a portion of that is ensuring that those teams that have applied for this have also taken either the BEAM or the MC squared training, and then additional $4,000 if they're able to be 20% less than the 200 kilograms of CO2 equivalent per meter squared. And then there's the up to $8,000 for the stream 3. So I think I've gone a little bit further than more detail than I would have I had planned for here already. So I'll let Frank take over. But this is I will put a link in the chat. Everybody can take a look in more detail and see a full webinar that we provided almost a month ago now. So the EOI the expression of interest has closed for this first round, and we're going through those applicants right now. And there'll be a new one that's opening up on July 13th. So you could, again, go through this data. If you have any projects that you see might be coming up over the next, 4 or 5 months, be on the lookout to apply for our next round here.
Excellent.
Okay.
You want? All right, want to share? All right, let me just get my screen up. And now let's kind of learn, I guess, about kind of, some cheats or some ways you can apply for some of these low embodied carbon drawings. So low cost, low carbon, made in Alberta building envelope assemblies. Do they exist? Can we find them? So yeah, construction used to be so simple. We just had to worry about schedule, quality, and cost. And unfortunately, even back then, it was kind of tough. It was kind of like pick 2, wasn't always pick all of them. But now we have to look at more things. So we are starting to look at how do we include durability, which is kind of those higher tier energy codes, how we improve energy efficiency, which is also those codes help us with operational carbon, embodied carbon, and then fire, flood, and hail. So those are some of those environmental risks that are definitely becoming more prevalent. Even if you're not sure if they're coming, your insurance companies know they're coming, and they are starting to change your costs of insurance depending how you react to some of those constraints. So lots more constraints we have to deal with. And then finally, we want to make sure that all this stuff is it available in Alberta? Because if it isn't, then it's really not that helpful to us. And then kind of the overall goals, we're applying all of these good design processes and overlapping constraints, and we want to actually end up with a building that is comfortable. So what did the grant do? The grant was to look at some low embodied carbon materials. So what did we use? There is that BEAM tool that Juan mentioned. We actually ended up using the MCE squared tool, which that is the tool that works right off of HOT 2000. So if you have a HOT 2000 energy model, you get the basically all the data gets directly imported to that MCE squared tool and just makes the kind of data entry simpler. Both of them are cradle to gate embodied carbon calculation tools, and they all build off of that growing list of environmental product declarations. And really, both of them are just a big Excel spreadsheet. So they're really not that difficult to use. A few hours of training, a few hours of playing around with it, you will be able to pick it up and get some usable, informative results out of it. So for those fire, flood, and hail, we use the Institute of Catastrophic Loss Reduction, nice big long acronym. They have a new resiliency tool, and that resiliency tool is designed to assist designers in selecting some assemblies and help them make decisions to make better choices versus poorer choices. So they just came up with kind of a good, better, best rating for various options within various different potential risks. And the risks that they looked at were extreme heat, smoke and fire, floods, hail, and high winds, water shortages and droughts, and slope stability. So depending on where and what your project is, you might have all of them or a few of these risks that might occur. And then you can go and look at that good, better, best rating system to see what products, materials, processes they recommend that you use. Okay. So once we start talking about these low embodied carbon materials, let's start with the big elephant in the room, and also the easiest one to change is low carbon concrete. So concrete produces about 8% of the global carbon dioxide emissions in the world. So it's a pretty big chunk of the pie. And because of that, over the past few years, concrete producers have responded with a number of what they call low carbon mixes. And really what they're doing, they're using supplementary cementitious materials to replace the cement, because it's actually the cement in the concrete that is the highest carbon emissions equivalents. There is breakdowns by province. So this is just a screenshot of the Alberta Ready Mix Concrete Association. So you should be able to call up your local ready mix supplier. This is the one from Lafarge. So inland Heidelberg should have the same one. Burnco, some of the smaller ones, should also still have availabilities. And here you can see that just by looking at two different EPDs that have the same strength, so all the same performance criteria, but they have a 10% carbon reduction. And because concrete is a fairly cost competitive industry, these lower concrete mixes don't cost much more. They're probably very equivalent cost. In Alberta, the easiest one is just swap out your cement for high fly ash. We've been doing this in Alberta for a number of years because we have a good fly ash availability. So if you do nothing else from this presentation, please, next time you buy concrete, ask for the low carbon mix. That will get you kind of the first step in kind of reducing your carbon on a building. So now let's look at some other options. So what we did is we basically took a whole bunch of common assemblies and broke them down by where the assembly is, and we gave them a R value, the nominal R value. We gave them an embodied carbon number, and then we kind of roughly rated them with cost, fire resistance, durability, flood resistance, hail resistance, and those three colors are just represent the good, better, best, or lowest, medium, high costs. So starting at the very bottom with the slabs, there isn't a lot of options for our slabs. Kind of the current standard is that just 4-inch concrete slab, no insulation, which isn't a very good idea from a thermodynamics point of view. So ideally we add at least 4 inches, possibly 8 inches of EPS, so you can see the R values go up. And then we also included the SI Construction. They have a polycore R slab, and it is a concrete-free slab. Still gives you some of the structure, but most of the structure is on the walls. It gives you enough structure on the floor, but it doesn't use any concrete. So as you can see on that, the embodied carbon number of the SI Construction Polycore R floor is actually less than just the 4-inch concrete. Fire resistance, obviously 4 inches of concrete gives you better fire resistance than the Polycore floor. Durability, they're all fairly good. They're all fairly good for flood resistance, and hail and wind resistance really is an issue with slabs. So let's move up a little bit more. Let's talk about some foundation assemblies. And now there is a much larger list, and this isn't a full list. This is just a list we have done so far. So if you're interested, if you're a supplier or you have your own kind of assembly that you like, by all means, reach out to us at Passive House Alberta, and we will add your assemblies to these lists, and they will eventually get posted onto MBEX or other websites. So with this foundation assemblies, there's a lot more options. Again, we can start with just your basic concrete foundation wall with interior insulation, either 2x4 or 2x6. Then we can go to a insulated concrete form with various thicknesses of concrete cores. Then SI Construction, they also have their no concrete foundation wall, which is called the Polycore wall, various thicknesses. And then another local Alberta company, SI Construction, is in Edmonton area. There's also ZS2 Technology. They make their tech panel, which is 2 magnesium oxide boards with a spline of wood. And we did those options. And then we did also the pressure treated wood foundation options. So here you can see we did various different nominal R values. The embodied carbon numbers can vary significantly. The pressure treated woods, because they're wood, no concrete and no steel, are generally the lowest numbers. But those SI constructions and Z2S aren't that much higher. Costs do vary a fair amount. Fire resistance, durability, flood resistance also varies a fair amount. So in this, it is a little bit difficult to find one that does everything perfectly, but depending on your priorities, you can find that one does the most things as best as possible. So now let's look a little bit more in detail on two of those assemblies. First, we'll talk about the SI construction polycore slab and wall. So essentially, it is a EPS foam with embedded steel studs. So the steel stud is all the structure. On the floor, they add a layer of tongue and groove plywood to give the structure to hold it together. On the walls, there is no sheathing needed. That the structural steel has all of the structure. And then this is part of our screenshots from the printout from that MCE squared tool. And it kind of shows you the main areas or the 7 most carbon intensive materials. Below that, we showed what we actually did as a wall assembly. So we made a kind of standard wall assembly. We made it 100 feet long just to get some numbers that were large enough. And that was included. And then you see below it the actual carbon number. So it's 3.5 net carbon footprint. Some materials have either short or long-term storage. The SI polycore system doesn't, because that long-term storage is generally organic wood materials. So both of these, or the foundation wall, could be used above grade, but we believe that there's some lower carbon options for above grade. But this is a very good low carbon below grade option. Another one is that ZS2 Tech panels. Again, here you can see the drawing. So they have their proprietary MgO magnesium oxide board. And the really nice thing is that magnesium oxide board actually has an environmental product declaration for it. And I believe they are the first MgO manufacturer in the world with an environmental product declaration. So cheers for them for getting that. You can see the list above on where the carbon intense materials are. So there is still two 2x4 or 2x whatever splines. That spline is basically what connects these panels. This is basically a prefabricated system that comes in basically 4x8 sheets. And every 4 foot, you have those 2x4 splines that allow you to connect the 2 panels together. So there is a number of materials that add up to the overall assembly's carbon content. So again, you can't just look at one product. You have to kind of look at full assemblies to make a better, clearer comparison, and ideally also looking at the same effective R values. But again, very good low embodied carbon number, can be used below grade, can also be used above grade. Okay, so now let's move another layer up. Let's move to those above grade wall assemblies. And again, we have a long and incomplete list that we have tested. Reach out if you want us to do some more testing. So we started with that kind of typical, well, it's not even typical because it's, it is a typical one. It has nominal R22, but really only effective about R18. And that is our 2x4 or 2x6 assembly with R22 bats in it. So it's very low cost, not very fire resistant. It's not very durable because it has definitely some condensation and mold issues, and it's not very flood resistant. And for all of these assemblies, the wind and hail resistance is really more related to what you use for the cladding than the actual assembly behind it. Okay, so going on for some of the other assemblies we looked at kind of a fire rated assembly, which is just that 2x6 wall, but with 2 inches of mineral wool on it. Then we move to some double stud walls where we have an inner and outer stud, either with fiberglass bats in between the studs or with dense packed cellulose between the studs. Now, once we add in that dense packed cellulose, cellulose is a carbon storing or a negative embodied carbon material because it uses recycled newspaper. So we can actually start to see some negative embodied carbon numbers for that assembly. Then there is the Savic dense packed chopped straw prefabricated panel. So it's using chopped straw that's dense packed into basically a double stud cavity, and straw is even more carbon negative. So those numbers drop again. And then we did some quick therm products. So quick therm is another type of insulation. It is made in Winnipeg, so not quite in Alberta, but pretty close. And it has foam, some film strips, and some embedded wood strapping on it. So again, costs can vary, but most of the costs are actually pretty comparable. There's no red costs here. They're all greens and yellows. Fire resistance does vary. Most of them are very durable, except kind of those kind of code minimum ones. And flood resistance, none of them have great flood resistance, but hopefully the water isn't rising too hard to get above to get too high and so the water doesn't get too far up your above grade walls. All right, now let's look in a little bit more detail in some of these assemblies. So first of all, the grandfather of the high performance wall, the double stud dense pack cellulose wall. So again, here is all of the printouts from that MCE squared tool. And what you can see is because we're using cellulose, that carbon storing material, in addition to having the 7 highest carbon emitting materials, we have the top 3 carbon storing materials. And that's where that cellulose comes in. And because it's on NBEX, that little SketchUp model that's shown there is part of NBEX's building assembly virtual library or virtual assembly library. So you can go on to NBEX, look in their resources page and get all of the details on this assembly right there. So you don't even have to think up how to use these double stud walls. And so it has minus 0.4 on the net carbon, and you do see that there is the short and long-term carbon storage. That's just depending if you're accounting for some of the longer-term storage in the solid wood products. But by default, we do not account for those because you really have to know how that wood was managed, if it's a sustainably managed forest or not. So that's why it's not included by default, but you could include that short or long-term storage if you wanted. And then the next one down is the Savic prefab straw panel. So Savic is a small prefabrication shop. They are located again just outside of Edmonton. They're using basically a double stud assembly, but they are collecting the waste straw from their farmers' fields. And straw is not hay. Hay is nutrients and animals eat it. Straw is the non-nutritional, basically inert stalk below wheat and barley. So we grow it for the wheat and barley, but that straw stalk below is essentially waste. A little bit gets used for animal bedding, but most of it is basically a waste product. Some of it does also get returned to the land as fertilizer, but there is metric tons of straw surplus. So that's why it's a good circular product, and it also has, based on the EPDs, even higher carbon storage. Because you can see here, there are the positive, and the bottom, there's that straw bale, which has a fairly large carbon storage, and there's also some wood fiber board on this one. So this is one of the most carbon storing assemblies that we found. Let's move up a little higher now, and let's talk about roof assemblies. So again, there's not a lot of roof assemblies. Basically, the 3 that we found that we've tested, and if we've missed any, by means, reach out to us. So there's a loose fill fiberglass in a vented attic. This is kind of your common lowest cost assembly. Then we go to loose fill, but instead of fiberglass, we have cellulose blown into the vented attic. And then we also looked at the Savic dense packed chopped straw. In addition to walls, they also make cathedral ceiling panels. Z2S also makes cathedral ceiling panels. So the costs all still are fairly low. The fire resistance, the straw is slightly more fire resistant than the cellulose and the fiberglass just because it's dense packed. All of them are very durable. None of them are really flood resistant, but to be honest, if the flood reaches the roof level, your house is probably a write-off anyways. And the straw, just because it's dense packed in there, has a little more inherent wind and hail resistance than cellulose and fiberglass. But again, for that wind and hail resistance, we really should be relying on that roof membrane. And these are all the same nominal R value of R60, and then there's shown the embodied carbon numbers. So let's again look in a little more detail. This is the vented attic truss with loose blown cellulose. So this should be kind of the default. This is one of the lowest cost because cellulose is a very low cost insulator. Some tricks when we are doing this type of vented attic is we want to make sure, sorry, we want to make sure that we are having a what's called a high heel energy truss. So that just means that the very edges, the perimeters of the roof trusses don't come and touch the wall below. We can maintain that same thickness of cellulose throughout the whole depth and the whole width of the roof. We still need to make sure we're having good ventilation. So we might need to extend those ventilation baffles so that they make sure they are above the cellulose depth. And we're bringing ventilation in from the soffit, past the insulation, then out through the attic. Other than that, it's pretty typical what you should be using most commonly. Again, there are some carbon positive materials, but we throw in that loose blown cellulose and we get a fairly good carbon negative number. And again, there is still that short and long-term potential from the wood framing. Okay, now let's move up even further, all the way up to those roof materials. So we did look at what type of roofing materials we wanted to use, especially as we're starting to bring in those other resiliency metrics or considerations, because that's really where it does make a difference. So cheap asphalt shingles are cheap. They're kind of still fairly low embodied carbon at 0.9 tons. They are the lowest cost. And fortunately, if you buy the lowest cost shingles, you're going to get the lowest fire resistance or no fire resistance. The first hailstorm is going to destroy that roof, and no flood and no wind resistance. So in some places and different little places, again, your insurance are going to start requiring you to use higher quality, higher durability, higher performance shingles. They can have higher class ratings for both wind and fire resistance. And once you start using those higher rated shingles, obviously the price goes up. So then we compared it to what we kind of see as the better option for our roofs. That would be a metal roof. So it is a big jump in embodied carbon from 0.9 to 2.1. Cost goes up a little bit, depends on your local jurisdiction, but the fire resistance goes up, durability goes up. Most metal roofs are warranted for 40 to 50 years, and the wind and hail resistance also goes up. You might get some dimpling in a metal roof, but other than that, the hail will not go through it. And then the third option we looked at, because we still like on-site renewable energy generation, which means on-site solar panels. So we looked at different ways that you can mount those solar panels. So the bottom line there is that standard aluminum PV racking, and even just that aluminum PV racking has about 0.1 tons of CO2 emissions for the kind of generic size that we picked. It's aluminum, so it's not going to be damaged. And the solar panels themselves generally have about a 2-inch size hail resistance, which is pretty high. So the other one we looked at, which is the newer one, which you might not have heard about, are called Che frames. So these are being imported from Europe. They've been around in Europe for a number of years, and they are basically a plastic and steel frame that you then mount your solar panels directly on. And we didn't have an EPD for it, so we have to use materials, and we did come up with a embodied carbon number, and it's closer to those shingles numbers. So it looks a little more detailed, that Che frames. So they are an example. Sorry, they are an example of a building integrated photovoltaic system. It consists of plastic and some stainless steel and a few other materials. So we had the masses of those materials, and we were able to enter them into the embodied carbon calculator to come up with that number. And basically, the advantage of them is they replace the actual roofing material below it. So as you can see here, below those Che frames, you don't have shingles, you don't have metal deck. You still have the waterproofing and a ventilation space, but you don't have the materials below it. And then the solar panels just get mounted directly to us. They're still set off the ground enough so you still have ventilation underneath it. Ideally, where we kind of see this used the best is on a cathedral ceiling, where you would have a larger 2x4 ventilation cavity above that cathedral ceiling or prefabricated envelope. So you have that 2x4 depth of ventilation, and you can see that the frames are open, so you get lots of good cooling below the solar panels. And then it sits very flush with the roof membrane around it, so you don't need the metal critter guard, and it just has a much flush, cleaner look to it. So where we see this being the most used are those cathedral ceilings. If you have a just cheap asphalt shingles, shade frames are going to be more expensive. But if you're going to that metal roof membrane, then not having to put that metal roof membrane or metal roof underneath the chave frames makes those chave frames much more cost effective. So it depends on what your kind of roof material that you're comparing against based on the overall cost effectiveness, but we do see that it is a lower carbon option in most cases. Okay, so now let's kind of put some of these products together, or I will show you a case study. This one is funded by SSRIA, their tech accelerator. I can't remember the actual program, but SSRIA funded this project. It's called the Conrad Garage Suite. It is a garage suite, so kind of 2-car garage and some storage with a 2-bedroom, 1-bath suite above. It fits on a 50-foot lot in Calgary. And we did both a kind of code minimum embodied carbon calculation and the proposed or as-built one. And as you can see, we went from about 17.2 tons down to 1.2 tons. So that's a 93% reduction in embodied carbon that is possible and achievable in this project. So what did we use? Well, here, first of all, this is the project specific material carbon emissions. So it shows you kind of where are the big negatives and where are the big positives. So again, this is another output from that MCE squared software. So starting at the top, you can see we're using bamboo. So bamboo flooring is very carbon negative because that bamboo, again, pulls the carbon out of the atmosphere, puts it into its cellular structure, and then you take the bamboo process and put it down on the ground. Bamboo does have a bit of premium, so if you don't want to pay that premium for bamboo flooring, you could also look at cork or linoleum. Both of those have also a slightly negative, although not as big a negative number. Then obviously the roof and the walls were the big negatives. We used the Savic wall panels for both the wall and the roof. And then for the foundation, we use the SI Construction Polycore wall and the SI Construction no concrete floor. And normally it has one layer of 3/4 inch tongue and groove. Because this was a garage and we needed to be able to drive a car on it, they just needed to use 2 layers of tongue and groove pressure treated wood on the floor, and that allowed you to drive a car on it. So you still don't need any concrete on the slab. The building still needed a small strip footing. And even that strip footing was fairly small. It still ended up being the biggest carbon addition. So this is concrete, standard concrete. We were able to order the low carbon concrete on site. So later on, or the final reports from this project, we will show you the actual as built, and hopefully that footings and slabs number will get even smaller. And then there's a few other various numbers. None of the big numbers. The big numbers are generally the concrete, and if you can do the big negatives using either straw or cellulose. Okay, so now let's talk about budget, because no one's likely to use the low embodied carbon materials unless they are kind of cost competitive, and that's really what we were looking for in this kind of research project, that we could find those cost competitive products. So for the Conrad Garage Suite, the budget was about $4,500, or sorry, $450,000. But this is essentially a 1,500 square foot slab on grade home, because the main floor, even though it's a garage, it can also be designed as a workshop because the insulation values on the main floor is the same as the suite above. and the main floor could be turned into a suite in the future. So what does that work out to? Nicely works out to $300 per square foot, which we believe is in the same range as what kind of code minimum buildings would be being built to. Obviously, that range is larger, maybe down to 280 to 340, or I've even been hearing $400 and $450 per square foot recently. So we think it's in the same range, but included in that number are about $21,000 to upsize the water main, which is a requirement if your water main is less than 3/4 of an inch. When you add a suite to it, the demand from just the additional people makes you have to go up to 1 inch, and that's about $21,000 to do that in Calgary. And it also included $35,000 of those solar panels on the roof because they use the Che frame roof system, but that makes the building basically net zero on-site energy. So if we exclude those two numbers, we get down to $263 per square foot, which is, we think, a very cost-effective number. This is all preliminary numbers. And obviously, if we're looking at cost effective of kind of additional dwelling units, it's all about the income and the expenses. So the first occupant of this garage suite is going to be the owner's mother-in-law, and they're currently paying about $2,500 for an assisted living room. Not a full needs, but still some assisted living. So the kind of cost effectiveness of this building will be reviewed as part of the kind of final report. And really, it's going to come down to what type of rent you would be able to rent it out for, on how fast this can be cost effective. But we do think that these low carbon materials are cost effective options. Now let's look at another example. So this is from an estate home, so a larger rural estate home. This is the actual pricing from it. So again, it was a high performance home, had some high performance goals, but no specific embodied carbon goals, but we still looked at different types of assemblies. So starting at the bottom, that slab on grade. So the basic was we used 8 inches of concrete and 4 inches of concrete and 8 inches of EPS foam below it. And then the alternate was using that SI Construction Polycore R slab option. As you can see here, the cost for the R slab was actually less, about $5,000 less. And it was also not as thick because really all of the insulation is used. You don't have that concrete thickness plus the insulation thickness. So we saved a bit of excavation. The R value was a little bit lower because the steel studs at the top of the SI Construction do reduce the effective R value. But then when we went back to the energy model to see if the change from R40 to R34 made any impact on the overall energy performance, and it was very minor. So we decided to stay with the R floor at R34. We could have added more foam, but we didn't see any improvement or any need for doing that from the energy model. So in this case, our lower carbon, roughly equally performing option was lower cost. Now let's move up to the foundation walls. So we looked at 3 different options. We had an 8-inch concrete wall with 8 inches of EPS foam. All 3 of these walls are all R40. Or we had a 13-inch ICF with an additional 4 inches of EPS, because most standard ICF walls are only about R25, and we needed R40. And then again, we looked at that SI Construction Polycore wall. It only needed 12 inches to get to R40. And again, it was kind of right into the prices. It was slightly more than just the concrete wall, but because we're using the foundation of SI Construction, made sense to also use, so we're using the slab as SI Construction, it made sense to also use the foundations, and it allowed to install quicker because there wasn't the concrete pour, and it's getting concrete to this kind of somewhat more remote location. It was always a bit of a logistics challenge. Now let's move again 1 level up to our above grade walls. And here we had 2 options. We used that SI Construction Polycore wall, and we used the Savic prefab dense pack straw walls. And we also had a double stud fiberglass wall. So the double stud fiberglass wall was the cheapest, and it was about 13 inches thick. The interesting thing is what we did is for those Savic walls, because it's using straw, which is a waste product, we actually got a quote for both an R40 wall and an R60 wall. And the interesting thing is, because that straw is essentially a waste product, the cost from going from R40 to R58 was really only about an additional $8,000 or $9,000. So if we just compared R40 to R40, the Savic wall would be very close to that double stud fiberglass wall, but we got 50% more insulation or 50% higher performing wall for just about $9,000 more, bringing it up to $64,000. And 16 inches thick, but we're on a rural acreage. We had acres, wall thickness didn't make any difference. So in this case, the owners decided to spend a little bit more, about $9,000, to get 50% better above grade walls. Pretty good return on investment, I believe, there. Now let's go to the top. Let's go all the way up to the roof. So here for the high performance, we wanted R90 wall, or sorry, R90 equivalent. So we looked at the Savic prefabricated cathedral ceiling panels and just our standard vented attic loose blown cellulose wall. And here the cellulose was again about $9,000 less. And because they're both the same R values, we decided to stay with that lower cost option of just the vented attic instead of going with the cathedral ceiling. Various different kind of reasons for that. I think cost was probably just the largest one. But if you are planning to build and you're kind of going into the winter season, there are some other things to think about. If you have to build that on-site truss system, that will take maybe 3-4 weeks before you get enclosed. If you went with a prefabricated system, either Savic or any of the other prefabricated systems or panelized systems, as soon as those panels get installed and taped, you are basically airtight and insulated. So if you're starting to kind of creep up into those winter seasons, that's where full panelized or full prefab modular makes more sense than building it on site. But again, both of these are low carbon options. The straw was slightly more, but the cellulose was still very carbon negative. And this time they took the cost savings on it. So kind of to wrap up, hopefully some of these low carbon, low cost assemblies are of interest to you and you start looking at using them sometime in the future or your next projects. But when we start to think about carbon, one of the biggest things we need to always remember is step one is just use less stuff. Building nothing, building less, building clever, retrofitting, renovating, not building new. Building new should be kind of our last option. And then when we do that, then we want to make sure we are using the low carbon materials on it. If we don't do this, then what we're going to kind of likely fall into is what is called Joven's paradox, which is where as the cost of something gets less, we actually end up using more of it because it's cheaper. So as we keep kind of falling into this over and over, as we get more energy efficient or improve the performance of something, we end up just using more of it instead of less because it costs us less. So final kind of comment on kind of sufficiency, housing, and use less stuff. This is a graph of the size of single family homes in Canada and the US over time. There's only 2 dots from Canada, but it shows that from 1970 to basically 2010, the average size of our single family homes has doubled from 1,000 to 2,000 square feet. And in the US, it's gone even higher. So this Joven's paradox could be an example of this. As costs go down, we just end up using more. But ideally, or if we don't start to kind of change this trend, low carbon, low cost, energy efficiency, none of that is going to allow us to solve the problems of just overconsumption that lead to climate change and some of the other various crises that we are currently facing. So with that, I'll end it. And we still got 15 minutes to discuss, because that's kind of always the part I like best about these webinars is the discussion. So let's see. All right, Lauren's asking, with an R90 loose blown cellulose, would you require OSB at the ceiling level to structurally support that much insulation, or is it just drywall acceptable? So Cellulose, because it's loose blown, even at the R90 or 3 foot level, we generally don't need any more than a membrane. Ideally, we are moving away from just a plastic poly vapor barrier to a more vapor open or smart vapor barrier. And generally those have better structural resistance. The other ideal is if we are doing any vented attic to make sure that we aren't penetrating those membranes, let's try to add an installation cavity below it, maybe a 2x4 installation cavity. And then that 2x4 installation cavity could go perpendicular to the trusses that would again support the additional load of the cellulose. Or you could use 1/2 inch or thicker plywood or OSB, because 1/2 inch or thicker OSB and plywood, when the joints are taped, are a code compliant type 2 vapor barrier, and it would give you all the structural support that you need. And then your drywall would just be below it. So yes, depending on how thick, you might need to ask your structural engineer, but we haven't seen that needed very often. If anyone has any questions, feel free to just unmute. Tim follows up with using type C drywall, which I believe is just a higher strength drywall designed for ceilings, is another good idea. Does anyone have any other assemblies that they think we should look at? Or do we want to kind of talk more about maybe some of the different fire-related or costs on these? Has anyone ever kind of used the beam tool or the MCE squared tool, or is this kind of all new to most of the people?
I had one question, I guess, just kind of based on the tools, and I don't know if it's I feel like it's something when you go deep into, it's like the biogenic numbers that you can use in some cases. So like let's say for like the Savic products, like are you kind of taking that into account in terms of like the EPD that would be used in like I guess like that first negative number that you would get, and when you're building like your scope there for those calculations. Um yeah, I guess like in that first EPD, like do they take that biogenic number as part of it?
So for straw and cellulose, they take the biogenic because it is a recycled product or a waste product,
Yeah.
where the that's where the net comes in. The storage, the long-term and short-term storage that is shown in these tools, that is basically the wood. So the 2x4s, the plywood, the OSB. And the reason that they don't include it by default is because we don't know where those 2x4s came from. We don't know if the forest that they're harvested from is sustainably managed. So FSC certified plywood and 2x4s, you could probably make a better argument that you can include some of that 2x4 and wood. But if it's just any random, we don't know where the 2x4 came from, then what has kind of been determined is that best practice is basically to just have it zero. It's not a carbon positive, but it's also not a carbon negative, because we are taking that carbon from the tree. And the comment is that if we left the tree there, the tree would continue to grow and continue to sequester more carbon. So unless we are kind of sustainably removing the trees and still keeping the forest healthy, we don't want to kind of pull the carbon somewhere else and then take advantage of it later. So cellulose and some biogenic materials that are waste products, you get to account for them right away. The 2x4s and other wood, you generally.
Okay. Yeah. As long as like they're saying like basically if it was like FSC wood, which there may be a premium on, but like that's the only time you would really take into account then.
Yep. Yes.
Yep.
So that's why it shows it. You can, within the tool, you can basically just click a button to include either the short or long-term carbon storage in your numbers. You would just have to kind of justify that with whatever program you are submitting your numbers to.
Yeah. Okay.
Frank,
Yes.
just gonna ask about the concrete-less slab
Yep.
and a couple questions. So first of all, how many people were pretty hesitant in going that direction? And how is it standing up to vehicle use? And in your opinion, would it be better to use the SI system or the system that you did use for the garage for the concreteless?
Yeah, so for the SI construction, we actually both of the projects, the Conrad Suite and the kind of estate home, both use the SI slab floor. It won't feel as hard as concrete because it isn't concrete, and they generally recommend that you put it on a full bed of sand just so that you have kind of full bearing on the foam. Otherwise, it could feel the worst that can happen is it feels a little bit bouncy or a little bit squishy, but that's not often a problem or not. The other nice thing is because there is no concrete, if you do have any problems with the floor, you just unscrew the plywood and can lift the floors up because it's just basically 4x8 panels. The plywood goes down, gets screwed to that embedded steel, and that's what gives you the rigidity. In the Conrad Suite, where we have 2 layers that a car drives on it, we're not occupancy yet. We're still kind of mid-construction, but I've been on that floor and it feels kind of almost as solid as a concrete floor to me. And yeah, it would just depend kind of where your preferences land. If you know it's always going to be a garage suite and you know it's going to be, or it's going to be a garage and there's always going to be cars on it, then maybe you don't need to insulate it at all. For the garage suite, that garage, 80% or 90% of the time, it's actually going to be a workshop. The likelihood of them backing a truck in to unload some material is fairly low. The rest of the time is it's more of a workshop. So that's why we insulated it. And then the not quite as rigid, not quite as flood resistant as concrete wasn't a concern. So it really kind of depends on what the actual use of the floor is going to be. But yeah, we've installed a few of them and they went in fairly quick, and we haven't had any negative feedback yet, but it is still a newer product. We're actually kind of looking at, could we combine maybe the ZS2 MGO board, not the full SIP panel, but just the board, replace that with the plywood here to give us a little more rot and mold resistance on that R floor. But we're pretty comfortable if we just put in some type of resilient flooring with the seams sealed like linoleum. It's pretty durable. Then the water should not get down to that plywood below, and it is pressure treated plywood.
Okay. Did you ever think about using pressure treated sleepers underneath the plywood? That kind of system with insulation?
So kind of like a pressure treated slab as opposed to a pressure treated
Yeah.
wall.
Yeah.
We looked at it, kind of basically the way this project was set up. It was a nice combination to have the SI construction walls and the SI construction floor
Yep.
as a system that's made in Alberta that we can kind of promote, that comes with all the engineering. There are lots of different options to do it. But yeah, that's kind of why we picked it for this one.
Great.
We like systems as opposed to having to think it up ourselves. What is the best way for manufacturers to get their EPDs listed? So the EPDs actually would not be listed with Passive House. Any manufacturer could go and get an EPD. Unfortunately, they still cost kind of $50,000 to $100,000 depending to create them, which is obviously one of the kind of constraints that we're still trying to work through. But once you create that EPD, then there are a number of different software providers, the MCE Squared and the Beam tool being kind of the 2 most prevalent for residential. Once you go into commercial, then it's kind of One Click LCA and Athena and 1 or 2 other ones. So once you basically have the EPD, then you just kind of publish it to as many different software providers as possible. And kind of the coordination of those software providers is kind of one of the areas that the kind of overall embodied carbon realm is still figuring out, because unfortunately a lot of those software providers, they don't like sharing because that's where they make their money. So again, there's a little bit of gatekeeping on some of this information, but any manufacturer could just publish that EPD on their website. And then you could also just bring individual EPDs as a user entered data into the software if it's not preloaded into the software. Looking through. Any other questions? Yeah, so again, going back to what Juan said, if you want to go for that stream 2, which is the embodied carbon calculation, you could use some of these assemblies. You should be able to talk to most of your energy advisors if they might already have some experience with the MCE squared tool, or if not, they can get training to become experienced with it. And it's really only maybe $2,000 or under to create this embodied carbon calculation for a whole project. Obviously, it can go up depending on how many iterations you go through. But really what we see, the biggest gain from using that tool is once you enter the assembly quantities, all of the EPDs are in the tool, and then it's very easy to compare that if I use product A versus product B versus product C, these are the impacts on my embodied carbon. And then you can kind of see what the lower embodied carbon options are. And then from your kind of knowledge in pricing, you could see where those kind of lower cost options kind of start to fall out. So that's kind of where we see it. The best use is use it right from the beginning. Just like all of the design, we need to be thinking about it at the beginning. Those performance metrics have to be there at the beginning, and that's when it can be the most impactful. If you've already bought everything and you're just finding out what you did, that's not helpful. We want to be using this to help drive our product selection. And if we find a manufacturer that has a very high number, but low price, you can tell them, I would have bought this, but your EPD is too high. So do better, and then I'll buy your stuff again. All right, any other questions? Then let me just save this or stop the recording.